In this lesson, we're going to see the final two concepts we need to complete the functional paradigm and its kernel language. There are two concepts: higher order programming and record data structures. So first of all, higher order programming is the ability to use functions and procedures, of course, as first-class entities in the language. So we can use them as inputs and outputs of other functions. We can have functions that are parameterized by other functions and that return functions that have new behavior. So this is an enormously powerful ability, and in fact it's at the foundation of data abstraction. So all of the sophisticated ideas of data abstraction and object-oriented programming, classes, object, metaclasses, inheritance, and so on, can be defined in terms of higher order programming. And after higher order programming, we'll look at record data structures, which are a very useful assisting concept. So they're a general compound data type. They allow symbolic indexing, so using symbolic constants called atoms. So this is useful for symbolic programming and also for data abstraction. So it assists very much in making data abstraction readable. So let's first talk about higher order programming. So higher order programming is based on two concepts. First one called the contextual environment, and the second one is called a procedure value. So we'll introduce each of them in succession. We'll first introduce the contextual environment, and then we'll introduce the procedure value, and then we'll show together the power of these two concepts. So let's introduce the contextual environment by means of a small exercise. So here's a little program. Local PQ, so I define here a procedure P. I define a procedure Q that calls P. I have here a local that's nested inside. I define another procedure P, and here I call Q. Now the question is, when I call this Q, what is displayed, 100 or 200? Does it call this P or does it call this P? So the P inside of Q, which definition does it call? What do you think? In order to answer this question rigorously, we need to find out the scope of the violet P that's inside the definition of Q. The violet P, so this zero argument procedure that we're calling inside of Q. So what is the scope of this violet P? The scope is that part of the program where all occurrences of P refer to the same declaration and its variable. So what is the scope? Well, here it is. So the scope is, it starts here from the local P. It then stops when we introduce another definition for P, and it starts again at the end of the inner local. So it's these two pieces here, this piece and this piece. So we're now looking at this P, violet P, the one that's called by Q. Inside the scope of this P, which definition is called? Which definition is referred to? It is this one. So we're going to display 100. So all of the violet P's here in the scope refer to the same variable, the one that's declared here in this local. Now, the procedure Q, therefore, must know this definition. And how does Q, when we call it here, how does Q remember that it's this particular definition that it has to call? Well, Q has its own little data structure stored with the definition of Q, which we call the contextual environment. And in the contextual environment, it stores the correspondence between this violet P and the definition. So, to be precise, the contextual environment of a function or a procedure, because they are the same in the kernel language, the contextual environment of a function contains all the identifiers that are used inside, but whose definition, whose declaration is outside of the function. So we saw also with Q how this works. Now let's see another example. Here we have a procedure inc, where it calculates y is equal to x plus a. Notice the a, this identifier here, is used inside the procedure inc, but it's declared outside. So a is part of the contextual environment of the procedure inc. So the contextual environment of the procedure inc is this function here, which makes the a identifier correspond to the little a variable, and this little a variable is going to be bound to 1 in this example.